Good afternoon, everyone. I'm Shengwei. I'm from Purdue. It's my great honor to be physically here to present our physical attack paper. Our paper's name is ImU, Physical Impersonating Attack for Face Recognition System with Natural Style Changes. This is a joint work by Purdue University, Nanjing University, Rutgers University, and Clarifai. When recognizing a person, a face recognition system first takes multiple photos with different poses. They are then fed to a neural network for recognition. A neural network can be used as a classifier. Given one image, it outputs a distribution of confidences over n labels. Or it can be a verifier. If the feature distances between two images are small enough, they are considered as the same person. Here, Takashi is correctly recognized. Now assume that I, as the attacker, want to impersonate the actor. As expected, a well-trained system won't consider me as Takashi. Our goal is to apply natural style changes to my face so that the system will recognize me as Takashi. Now let's see the threat model and attacker's capability. We assume attackers can utilize public face dataset to train generative models. Attacks can be set up in white box or black box setting. The former allows attackers to access the model internals and use the gradient-based optimization. While in the latter setting, when the subject model is a classifier, attackers can only access the output and use search-based optimization instead. When it's a verifier, we white box attack surrogate models, and they can be easily trained without accessing the private dataset. A common way to conduct physical attacks is first generating the impersonating faces in the cyberspace and then physically realizing it. There are 4 challenging requirements for a successful physical attack. The first one is that the attack method should be able to work with real attackers' images. For example, based on the real attacker's image, it should return an updated image that can fool the subject model and guide the attacker to physically apply the changes. Here we list the digital results of existing methods and ours. It's easy to digitally fool the subject model. However, not all of them can guide the physical attack. This is quite related to the second requirement. For example, exact pixel mapping and abrupt changes are not feasible. Among the 3 existing methods, ADV glass and ADV makeup print out the patches and attach them to the faces. While SAM-ADV proposed as a digital-only attack is not physically applicable because of the dispersed adversarial noises. In contrast, we generate natural style changes and ask cosmetologists to physically realize them. We also want the attack to be stealthy. Existing methods try to improve the stealthiness by bounding the perturbation in the pixel space with a certain norm or confining the changes within a small area. We claim those are not the necessary conditions, and instead, the stealthiness in the real world is highly related to the naturalness of the adversarial changes, because they are less noticeable or suspicious in humans' perspective. In this sense, strange glasses or patches is less stealthy. Last but not least, the applied change should be consistently effective across different poses and views. It's almost impossible for the attackers to ensure a certain pose when captured by a camera. Most existing methods are based on one single image or images of a similar viewing angles, and therefore the results are different for different poses. Our method utilizes StyleGAN to find the style changes. It has 2 networks, the mapping network F on the top and the synthesis network G on the bottom. To generate an image, a random noise Z is sampled from the Gaussian distribution and transformed to an intermediate W space by F. Then W is duplicated and fed to each style block of G to gradually shape the styles of the final image. If we feed different Ws to different blocks, we get an extended W plus latent space. Because of the semantic editability of the W plus space, StyleGAN is widely used for editing images. To edit an image X, the first step is embedding X into W plus space. Then we can change W with some delta to get the modified image. Here shows our high-level workflow. We first embed attackers' images into the W plus space. Then we find perturbations in W plus space such that the edited images can fool the subject model. Now let's dive into the details. To meet the first requirement, it's necessary to embed real attackers' images to W plus space. Here we show results of existing methods. The first row shows the real images. The second row shows the results of an encoder-based method. An encoder network is trained to map an image to a latent vector. The third row shows the results of an optimization-based method. It optimizes the latent vector directly for each image. However, none of them can faithfully embed the facial features and the poses at the same time. This motivates our embedding method. We observed that the 4x4 noises of a StyleGAN trained using unaligned dataset actually determine poses. By default, the noises are fixed after training the GAN. Now we explicitly provide the used noise. There is now x equals g of w and n. We visualize images generated by different pairs of w's and noises. Each row uses the same w vector, while each column uses the same noise. We can see with the same noise, different w generates different identities with the same pose. So let's leverage noises to fulfill the poses while letting the embedding procedure focus on the remaining features with the optimized w vector. We propose an algorithm to automatically select the noise for a given pose. Here we use a side face as an example. We approximate a face pose by the yaw angle and the roll angle. These values can be easily computed based on existing landmark detection algorithms. We first presample a set of images using the same W but different noises and compute the yaw angles. For example, the second image's yaw angle is 1.92. Then we compute the yaw angle of the real image, which is 2.56 here, and find the sampled image with the closest yaw angle. Here, the second sample is selected as a pose reference. We then align the real image to match the reference pose by rotating and resizing the face. We use the optimization-based method to embed the aligned image with the noise being fixed to N1. Great. Now we can solve the first challenging part by our proposed embedding with auto-alignment method. Let's see the results. The fourth row shows our embedded results. Obviously, we now can faithfully embed the facial features and the poses. After real faces are embedded, we need to find the natural and the consistent style changes to complete the attack. Without any constraints, we can go beyond the natural faces and thus violate the requirements. We use the standard deviation of each dimension of W plus space to statistically bound the delta to achieve natural changes. However, the changes for different poses are not consistent yet. To satisfy the fourth requirement of consistency, we choose to find the same perturbation direction D for images of different poses. Comparing the two rows, we can see that this change indeed enhances the consistency. Putting them together, it completes our workflow. Here we show the detailed workflow after the embedding when the subject model is a classifier. For the verifier case, please refer to our paper. Let's first look at the white box setting. Synthesis network G generates images based on the embedded Ws and the 1D to optimize. The images are fed to the subject classifier to get the largest output. CW loss or cross-entry loss can be used as the attack loss. The gradient descent-based optimization procedure are used to update D. At each update, we statistically bound the changes. The white box attack loop is highlighted in red. The black box attack loop is similar, except that now the network outputs the label prediction score instead of the logits. And we use search algorithm to update D. We evaluate our methods on several pre-trained classifiers and verifiers, as well as two commercial services. We compare our method with 3 existing baselines. Due to the time limit, we only show partial results here. This figure shows the effectiveness comparison when attacking a VGG16 model pre-trained on the VGG face dataset. It is measured by the attack success rate, ASR. That is how much of the generated images can be misclassified at the target. We also see the noisy effects in the real-world environment, such as the different viewing positions or dust on the lens. Results show that our method is the most effective. As for the naturalness, we use natural image quality evaluator and the total variance. We can see that our images have the best score. We conduct a human study to evaluate the consistency. We show two adversarial frontal faces of one attacker with different styles and another side face with either style. We ask the user to match the correct style. 95% of the users can recognize the corresponding styles of different poses. This figure shows we can successfully attack the Clarifai commercial service. To conclude, we studied the 4 challenging requirements for a successful physical attack. To deal with the first requirement, we propose an optimization-based method with auto-alignment to embed real attackers' images into the latent space of StyleGAN. We use statistically bound in the latent space to generate natural and physically feasible style changes to fulfill the second and the third requirements. To satisfy the fourth requirement, our method optimizes the same style change for a batch of the attacker's images of different poses. Our method can work in both white box and black box settings. Results show that our method outperforms existing baselines. Our code is available at this repo. Thank you very much for listening. I would now like to open the floor to questions.
Any questions? Yes.
Thank you for the great presentation. This is Yuan from the University of Michigan. I have two quick questions. The first one is I'm not so sure about the physical setup here. I guess my question is, why do you need impersonator image in the first place in order to generate the image for the thing? Because I guess this is related to my second question. So recently there have been some works by NVIDIA and Shen showing some real-time live facial synthesis technologies that can approximate the face of people very well by just using 2D images, for example. And there are also a lot of works from the CV space about synthesizing 3D images using 2D images. So I'm just thinking, what is the difference between those kind of works, completely synthesizing or recreating the face of a person between that and your work, and why do you need the impersonator image here?
Yeah, thank you very much. To make sure I understand your first question is asked, why do we need the target person's image here? No.
Okay,
the impersonators.
Right,
yes.
Because you're adding perturbations to the impersonator image, right?
So basically, why do I need my image to impersonate Takashi? Yes, because I, as the attacker, I need to physically realize it. If I don't have my image, so where is the starting point?
What is the physical setup here? So your camera is recording your own face, and how are you generating the perturbation here?
Yeah, so for example, the camera is installed by some authentication system. It's not controlled by myself. And I want to break into the system. I want to enter some kind of authorized zone. And then I need to kind of put the makeup on my face. So that's kind of impersonating attack. Yeah, but regarding your second question, yeah, I think it can be considered as synthesizing some faces which can fool the system, but at the same time, the distance between the synthesized face and the attacker's face kind of is close, so that it can be physically realized but on the kind of attacker's face. I'm not sure if that answers your question. Thank you.
Any other question? So let's thank Shengwei here. Great presentation.
Thank you.